Okay, so on the first one, factoring up top, you should get x, x minus 5, x plus 5. Okay. Cancels out nicely. Since we're taking the integral of this, would it be best to leave it as x times x minus 5 or to multiply it back through? Multiply it back through. Okay, so we're looking at the integral of x squared minus 5x dx. Tegan, what'd you get? What's the integral of x squared minus 5x?
The 1/3 x cubed minus 5 over 2x squared c.
Good. Nice. All right. Now on the next problem, find f if f prime of x equals all that and given f of 0 equals -2. If you have your derivative and you need to find the original function, what is that? How do you do it? Antiderivative or an integral. Either way is fine. Okay. We'll set it up as an integral just because that's what we've been doing in this chapter anyways. Oopsie daisies. Emily, what's the antiderivative of e to the x? Tegan, what's the antiderivative of 20, quantity 1 plus x squared to the -1? Okay. Then you still need that plus c. So this gives us our function so far, plugging in -2 for f of x, and then 0 for x. Emily, what'd you get c to equal? Good. So then Tegan, what's our f of x, the function they were asking us to find?
So it's e to the x plus we use the inverse of x minus.
Good. Just like that. Very good. Okay. Don't forget the plus c. Em, you got it? All right, so let's talk about initial value problems. We want to find f of x given dy dx and an initial value. So they're giving us the derivative and a value of the initial function, and they're asking us to find the initial function. What?
Does this have something to do with the next change theorem?
No, we're doing a few more examples and then we'll get into net change theorem. All right. So given our derivative, we're going to take the integral of secant squared of x dx. Now that y of pi over 4 equals 3, our pi over 4 and 3 are a and b on our integral. They're not. They're values that we'll plug in after we find our function. Okay? But that only happens if it's written like, if it was written pi over 4 to 3, then that's your a and b. But if they're saying that y of pi over 4 equals 3, it's saying when x is pi over 4, y is 3. All right, so what is the integral of secant squared of x? Tangent, okay? Since this is an indefinite integral, what else needs to go there? Plus c. Okay, so right now we've got f of x equals tangent x plus c. How do we find c? Plug what in for what? Put our 3 here, and then tangent of pi over 4 plus c. What is tangent of pi over 4? What, sweetie? 1. Good. So 3 equals 1 plus c, which means our c value is going to be 2. Then our f of x is going to look like tangent of x plus 2. Everyone okay with that? Good? T, good? So let's do it for this one. If I give you dy dx equals x squared times the quantity x squared plus 3x, and that y of negative 1 equals 4. So we're going to be using an integral again of x squared times the quantity x squared plus 3x dx. Do we want to leave it written that way? No. What should we do? Okay, and what's that going to give us? And? Good. Dx. Tegan, give me the antiderivative for that, please.
One-fifth x to the fifth plus 3/4 x to the fifth.
Good. Good. Am you alright with that answer? And then now what?
Negative 1 and 3x and equal to 4.
Good. So if you plug in negative 1 and take it to the 5th power, is it going to be positive or negative? So that's going to look like a negative 1/5. If you take negative 1 to the 4th power, what's that going to be? 3/4. And then plus c. Emily, what'd you get?
3.45.
What?
3.45.
3.45. Okay. So then our f of x is 1/5 x to the 5th plus 3/4 x to the 4th plus 3.45. Teague, you feeling okay?
Yep.
All right. Em, you feeling good? All right. Let's talk a little bit more about integrals with trig functions, okay, and having to deal with some fundamental trig identities. So let's take a moment and review fundamental trig identities. So let's just do a recall fundamental trig identities. What's the big one? Very good. Okay. The biggest one is that sine squared of theta plus cosine squared of theta equals 1. That is the most important fundamental trig identity. Everything else kind of stems from that. What?
I'll write this down.
Just watch, okay? You don't have to write it down. I'd rather you just watch. How did we find another one? Remember? That's what we called a variation. And yes, there is that if we wanted to say 1 minus cosine squared of theta. So like if we rearrange this to pull the cosine squared over, then that would equal sine squared of theta. Which is also the same thing, or true to say that 1 minus sine squared of theta equals cosine squared of theta. Those are what we call the variations. Do you remember another trig identity, though? One that didn't deal with sine and cosine. There was one dealing with cotangent of theta, and the way we got that was we divided all of these by sine squared of theta. Tegan, what's sine squared of theta divided by sine squared of theta? And then, Emily, what's cosine squared of theta divided by sine squared of theta? Good. And then, Tommy, what's 1 over sine squared of theta? Good. Okay. So there's our second fundamental trig identity. Tegan, as a variation, using some algebra, how else could we rewrite that? Usually, instead of moving the 1 over, like we would move the cotangent squared over, kind of a thing. So cosecant squared of theta minus cotangent squared of theta equals what? 1. Or you could do like 1 minus cosecant squared of theta would equal negative cotangent squared of theta. That one's not always quite so popular though. If we wanted it to be cotangent squared of theta by itself, what would that have to be on the right-hand side then? Good. So dividing by sine squared of theta got us the second one. What else could we divide everything by? Good. So if we divided by cosine squared of theta, Emily, what would your first term be? Keep going. Mm-hmm. Very good. So those are our 3 big ones, and then there's all the variations of them. So again, if we wanted tangent squared of theta to be by itself, Tegan, what would we have the right-hand side look like? Good. Okay. Going back to this. So if we want to take the integral, Tommy, go ahead and write this one down. It's an example. The integral of 4 cosine squared of x plus sine squared, 4 sine squared of x dx. Algebraically, Tegan, what can you take out of both of those terms? 4. What would be left inside? And what is cosine squared plus sine squared? 1. So this is just the same thing as saying take the integral of 4 dx. Are you okay with how that worked? So M, what is the integral of 4? Close.
1.
No.
1, right?
Oh, this is a fun game. What's the integral of 4?
0.
No.
1.
4x
Oh, I see it.
plus c.
Yeah. Oh, okay. I see myself in the door there.
There we go. Whenever it's a number by itself, you just stick an x on the end of it. Yes, you did. All right, so let's talk about tangent squared of x. We want to take the integral of tangent squared of x. We made that nice table that talked about all the indefinite integrals, but did any of them have a tangent squared on it? No, okay. So we're going to rewrite this as the integral of secant squared of x minus 1 dx, just using our fundamental trig identities. Do we know the integral for secant squared of x? Yeah, what is it? Just tangent of x. Okay. So the integral for secant squared of x is tangent of x. Now, what's the integral of 1? Yes. And then at the end? Very good. So using fundamental trig identities to find our integrals. Are you okay with how we did that? All right. Em, you good? Let's take a look at this one. If we have sine of 2x over 4 cosine of x, take that integral. Can we reduce the 2 and the 4? No, because the 2 is stuck behind or inside of a sine function, and the 4 is out in front of the cosine function. We do have what's called a double angle formula for sine of 2x. I would be so impressed if you remembered it.
Oh, what?
We have a formula, it's called a double angle formula for sine of 2x.
Oh, it's that
Or
one
sine
thing.
x, sine x, or something like that.
What is it?
Half of sine x, cosine x.
Not half.
I'm talking
Or
about.
something in front of it.
Oh, that's A's and B's.
No, you're thinking the alphas and betas. Although technically these were here
Maybe
too.
it's just 2.
It is, Tommy. Good job. So sine of 2x is the same thing as saying 2 sine of x cosine of x over 4 cosine of x. Algebraically, why is that nice?
You can cancel out the cosine.
Yes, the cosines. We can actually also reduce the 2 and the 4. So this is now going to look like the integral of 1/2 sine of x dx. So what is the integral for 1/2 sine of x? I feel like there's a negative there.
Cosine, yes.
So negative 1/2 cosine of x. Emily, it is 99% done.
Let's see.
Good. Just like that. All right, let's take a look at this one. Okay. Distributing that secant of x, what would that give you? Oh wait, didn't I tell you to do this on your own?
No.
Okay. Well, I guess we'll do it together. So this is going to look like secant squared of x. Ooh. C squared. No. Secant squared of x minus. What happens if you take secant of x times secant of x? Yeah, what you said. 1. Secant squared times cosine makes 1 because they are reciprocal functions. All right. Oh, hey, didn't we just do this one? What's the integral of secant squared of x? It's what? Just tangent. The integral of secant squared of x is simply tangent of x.
All that thing is secant squared of x minus 1 equals tangent squared of x.
But we're doing an integral. And you're right, it does, but it's easier to take the integral of secant squared minus 1 than to take the integral of tangent squared. There we go. Okay, so let's talk about some more of the net change theorem. And it's basically doing all of what we've been doing, just applying words to it now. So, one application of it, you don't have to write all these down, okay? But let's just take a look at them. Tegan, you get to read that one. Go.
The top thingy?
If V of t.
Okay. If V of t equals the volume of water in a reservoir at time t, then its derivative, V of t equals rate at which water flows into the reservoir at time t.
So, if we want to talk about the integral of the derivative, using our nice little fundamental theorem of calculus part 2, we take our antiderivative, plug in our things, and that's the change in the amount of water in the reservoir between time 1 and time 2. Okay. So we can use integrals to look at a rate of change, or a rate at which something's happening. Emily, your turn.
Okay, C of T equals the concentration of the product of a chemical reaction at time t, then the rate of reaction is a derivative d of C over dt.
So then if we take the integral of that, gets us back to our original function, and that gives us the change of the concentration of C from time 1 to time 2. Huh? Tegan, you're up.
I'll tell you my exciting news later, okay. If
Read
the
this.
mass of a rod measured from the left end to a point x is mx, then the linear density is px equals m,
Prime.
okay, x. Looks like a 1.
Get new glasses.
I tried talking to her, but she told me no.
I got apostrophe.
That I believe. It does not look like a 1.
Not like a weird one.
So then if we take the integral of that, okay, it gives us the mass of the segment of the rod that lies between your 2 points, A and B. All right. You're kind of seeing how net change works. You take the derivative and it's like, hey, this is the change of whatever's happening from here to here, whether it's a time or whether it's a location. So, where this is really nice is, it's just a bunch more things where it works. Position functions. Okay. Do you remember when we first started talking about a position function? We said the original function was the position, so S of t. Then if you took the first derivative, what did that give you? But what is that? Yes, but okie dokie. So first it's the position, and that's S of t.
A velocity.
Thank you. Yes. Okay.
Acceleration jerk.
Yes. Okay. Position, velocity, acceleration, jerk.
That's the name of it.
Ah, silly me. Okay, and then velocity is your first derivative, which we call, v of t. And then acceleration was your second derivative. OM, hang in there. And then, yes, then we had the jerk, okay, which we don't really use. Now, this is really nice with integrals because they start you with velocity and you have to work your way back up to the position.
Yay.
It lets you know what happens between time 1 and time 2.
My car passed inspection. Okay.
Okay, take a moment, sketch that, please.
My car passed inspection. It's fine.
Don't you have a couple things broken on that car?
Really.
Passed inspection today.
I might be getting a
Be happy.
2018. I'm happy.
What?
I might be getting a 2018.
A 2018 car?
Yeah.
Oh, I have one of those.
We get a Buick Enclaves that my mom's looking at.
Really? Those are supposed to be pretty nice. Why would you get it?
I'm spoiled.
No joke. As long as you know,
I'm okay with it too.
the whole going to court thing, that didn't take
Actually,
away.
you were more mad than my mother was.
I'm glad somebody in your life is disappointed in you.
My parents weren't as mad as Brett's because I actually told my parents that the day after it happened.
That was smart.
I feel like Gina knows everything.
They do. Mothers, they do. They just know everything.
Did I write the displacement?
Yes. And this is a typo. This is actually supposed to be distance. Okay. So the displacement is your integral of your velocity function, okay, where when it's above the x-axis, it's positive, it's your normal one. Where it's below, you're subtracting, doing what you gotta do, and adding them all together. When you're finding the distance, a distance is always positive. So that's why we have to take the integral of the absolute value of our velocity function.
same thing.
But they're thinking Ruby Tuesdays. And then, but like, you're getting your hair done at 2.
Yeah.
So I think you'd be done with everything by like 3:45. Because it's gonna take Nita like an hour to take pictures, she said.
Who else going in your group? Wait, keep writing.
Is it a line? It's a line. So it's us and then Cora and Wyatt.
Mm.
Yeah. Then we'd like eat at like 5, I guess. So that gives us like an hour to eat and then some more time and then that would be at the front of the line. Any thoughts?
Or maybe it's,
'Cause I don't wanna be at the end. It's like a board standing there.
And if your date's not interesting, that is pretty rough.
Ooh, that was savage.
Okay, so, that's great.
Oh, I'm pretty entertaining.
Emily and I are going together.
That I believe.
I'm just saying if you get bored with Matthew, I can be pretty entertaining.
So,
You have Brett though.
if
I don't find anything you've got bored.
W prime of t is the rate of a baby's growth in pounds per week, what does the integral from 0 to 2 of W prime of t dt represent? Take a moment, write it down, then we'll talk about what it means.
Missing a lot of this stuff.
What time?
I'm missing a lot of this stuff.
That's why I'm recording all of it, and I'm going to email it to you or post it on YouTube so that way you can go back and watch whatever you need to watch and skip over whatever you don't need. Like the girls' prom plans.
Pretty important.
Call me might need those.
Yeah.
Fair.
There might be a campus bowl question over them.
Yeah. What are Emily and Tegan doing
For
on
prom.
April 28th?
It could happen.
Yeah.
If that happens, you guys should probably be very creeped out.
Nope, I would be way impressed.
I'll be like, I know this.
I know.
Okay.
I guess one.
All right. Now, based on the way this is written, they're asking you to say what does the integral represent? It represents a net change, okay, in something. What is it that is changing?
The baby's growth.
Okay, the baby's growth between what?
Weeks.
How many weeks?
So it's say
0 to 2 weeks.
0 to 2 weeks. Very good. Okay, so that's what we wrote down. The net change in the baby's weight in pounds during the first 2 weeks of life.
Mhm.
Like, why did it go?
It went away.
Well, I'm trying to make it bigger so Tegan can actually see it.
I can read it, kind of.
Yeah, exactly.
Okay.
Off my paper.
How about now?
Can't read your paper. You're hunched over it.
Oh.
The net change in the baby's weight in pounds during the first 2 weeks. If you wanted to say from 0 to 2 weeks, that would be fine too. Do you understand why it is weeks?
Yeah, this is weeks.
Exactly. And do you understand why it's 0 to 2?
It says 2
And 0.
and 0.
On the,
Integral.
Integral.
good.
Bingo.
On the top.
I like bingo.
We play math though.
Can we do that now?
No.
With like addition problems?
I
That
had a
would be
rough
fun.
day. I got to went to court and find out I didn't need to be there.
I feel like you could have figured that out before going. You could have called and asked.
Well, I didn't think about it.
They just tell you don't need to.
I
be
did
there.
wonder why you were there and Leighton wasn't.
Yeah, because then
He was in
But
class.
it's like, yeah, my dad called it today and said that they're referring it to the Schuyler County Juvenile Officer.
So who do you gotta meet with?
Schuyler County Juvenile
I know,
Officer.
but like who is it?
Is that Kim? I think her name's Kim.
It's a female.
Yeah.
Who needs
I know
to-
Lucas Rhodes was always scared of her. So I thought she was good.
Have fun.
She's a nice, like, I never had any issues
I don't
with
feel
her.
like she's scarier than Gina.
Have you met her?
No, but not very many people are scarier
Watch
than
her like
Gina.
a scar down her face and be like,
Wait, I lost it.
I'll be like,
Okay,
I've seen her
so-
everyone.
If I prime of t represents the rate of change in your income in dollars from a new job, where t is measured in years, what does the integral from 0 to 10 of I prime of t dt represent?
you have to pay for court fees or anything, do
No.
you?
I don't see anything.
You will if you do it again, because now you're an adult.
Actually, Brett doesn't have to pay any either. So he has to do 20 hours of community service,
Okay.
and that's it. I think that's all we have to do.
Is this his first offense?
This was everyone's first offense.
I thought it was Leighton's second.
It is.
So then that means
He-
not the first.
Yeah, but it is. It's Brett's first.
Okay, well, you said everyone's.
Well, Layton was there. Everyone there that had to report, it was their first offense.
Okay.
So what is this juvenile officer gonna make you do?
I don't know. I haven't talked to him.
I'm really curious.
Who, is it your responsibility to contact her?
I don't think so.
I feel like it probably is.
No, Fisher said that they should be contacting me.
Oh, okay.
Is
She
there-
might be calling your parents then.
Okay.
Is there a way that that thing is getting these
I'm gonna
lines
talk
or?
to Gina.
Yes, everything that is on here is on there and being recorded.
Well, I think he's on 6 months probation too.
Okay,
Brett?
that's
That'd
a
be a
part of the
problem then.
screen.
Yes.
Ah.
Everything that I do on the screen, my voice, everyone's voice in here, everything that I write, everything that's already on the screen, it is recording. All right, so we are dealing with what?
Rate of change in income.
Not a rate of change.
And change in income.
The change, we're gonna be specific and say the net change. And it's not a real big difference, but we'll be picky. The change in, what?
Income
Uh,
in dollars.
from what?
New job.
0 to 10.
10 what? Good, 0 to 10 years. Nice. Okay, so the net change in income in dollars during the first 10 years at the job. Don't worry, we'll do some math next.
I'm good. We can do this a couple more times. I feel like this has been a really long lesson.
It was really a long day.
You haven't even been at school.
Yeah, I know.
Good luck doing the Bible.
Is that white people that come?
No, we're doing that next week. We're doing the foods that
Seriously?
Uh-huh.
No, I'm not
Why are
doing
we putting the numbers
It's this
on the
page
logo
packet thing, but we get to
It's
remember
both
both sides too.
now?
It's like on the Google
Above and
Classroom.
below. It's-
Google Classroom is like the website, but then you
We
choose
haven't
it.
bring it to the right.
It's at the bottom and at the top. It doesn't matter exactly if it's right on top or to the right of it. Your bottom limit and your top limit. Okay, so let's take a look at V of t equals t squared minus t minus 6. A particle moves along a line so that its velocity at time t is, boom, measured in meters per second.
I'm sorry, that was sleeping.
Yeah, that's fine. Write down the equation. And then on part A, write down displacement.
Good. I'm going to put stop and tell one on the back.
Wait, where exactly were you at?
Bloomfield.
That does not make sense.
Then we went to tell one on our way back.
That's the opposite direction
know.
of back.
I was like, wait, where were you at?
Why did you go to Ottumwa?
We were hungry.
There are places to eat in Bloomfield.
All I had was like a Subway and a Pizza Hut.
And
Yeah,
they
but
have
his mom works
South
there.
Fork, and they have the Mexican restaurant, and they have CJ's, and
She wanted Burger King. That's
We
what
went to Burger King.
that you drove all the way to Ottumwa for Burger King.
Well, I wanted to go to KFC, but they're like, we don't open till 11.
What time are you there?
10:40.
Kids there for 20 minutes.
No, we just walked over to Burger King.
Poor thing.
Okay, so first thing we're going to do is find the displacement of the particle during the time period from 1 to 4. So, what are we going to do?
Derivative.
Antiderivative.
That one. Integral from what to what?
1 4.
1 4.
Of what?
That
T squared
equation.
minus T minus 6.
DT.
Very good. Okay. Now, strictly speaking, that is called an integral, but we will evaluate it using our antiderivative method.
Mm-hmm.
Fundamental theorem of calculus, part 2.
So 1/3 T cubed
Yes.
minus 1/2 T squared
Yes.
minus
Yes, evaluated. No, not plus C.
Never mind.
Evaluated from what to what?
4 to 1, 1 to 4.
1 to 4. Okay, so that means we gotta do like f of 4,
I feel like maybe
Minus-
you could say the top number.
f of 1.
Yes, I wish so.
I mean, I feel like it should be.
Yeah, make more sense.
The one just says 1 4 is right to 1 there on top.
Figure out what f of 4 is, please.
Yeah, T, get on.
I think she's talking to you,
Nope.
Miss School Skipper.
Is it?
Is this county or Timmins?
I don't know. Probably. I didn't get a note. I didn't get a note.
You probably asked.
I don't know, but I mean, it's from the courthouse thing. I was like,
Oh,
She's like, can I have a note for that?
yeah, this one.
64 is like negative 10.67.
yeah. So negative 10.67 minus, now do f of 1.
Negative 4.5.
Altogether, you got negative 4.5? Okay.
Great,
Here's
listen.
the first second.
Well, the displacement, and it's kind of tells which way it's moving. So since it's negative, would it be moving to the right along the line or to the left? To the left, okay, so it's moving left. Now we need to find the distance traveled during this time. So it's an integral again, but how is it different than the displacement?
Distance,
Well, yes.
not the direction.
It's still going from 1 to 4, but instead of just taking the integral of v of t, you have to take the absolute value of your v of t.
Just be 4.5.
No.
Dang it.
No.
I tried.
You hope and pray, but no.
I want Lava Latte.
You just got Burger King.
I know I had Lava Latte yesterday too.
You're gonna
We
like.
need to know where it's greater than 0. So we have to factor it, see where it's equal to 0, draw a number line, pick points, do some shading, and then break up our integral
I'll
over
do
those
that in
pieces.
that
No,
one.
just an absolute value.
Hmm?
Right, do I have a number for that? Probably not.
I'm going to say no. I'll be honest. All right, so in terms of factoring t squared minus t minus 6, what does that look
T
like?
minus 3, T plus 2.
Oh, you did say t, and that is correct. So that means we're looking at 3 and negative 2.
Number 9.
So we got negative 2, 3. In between is 0. Do we care about to the left of negative 2?
No.
No. And then to the right of 3, 4 works. All right, so Emily, if we plug in 0, what does that give us?
6.
Negative 6.
Which one put in it? In that one, you get negative 6.
Okay, so no.
4 worse.
4 works. Okay, so we are positive here. We are negative here. So we're going to break this into 2 integrals. Now this integral starts from 1. Very good. Now that's the negative part. So that's going to have to be negative our velocity function plus the other integral will go from 3 to what? And since it's already positive there, it can just remain the normal v of t dt.
You know what more, right?
Yes.
Dang it. I know.
So
I know.
our integral from 1 to 3 of our negative velocity would look like negative t squared plus t plus 6 dt. And then the integral from 3 to 4 of the normal velocity, so t squared minus t minus 6 dt. So we need to find the integral of both of those things using that method and plugging in our numbers. Okay? Tegan, which one do you want to do?
Bottom. Actually, one to top. Never mind.
What?
Which way down?
This is more like left or right.
I have them up and down. Sorry.
Okay, so which one do you
I'll
want
do
to do?
this one.
Sounds good. Emily, you're doing the right.
Okay.
It says to me on my.
Fair. Yep, that's fine. And I need to give myself more space here. Are you getting 7.33 repeating? Okay, and then Emily, did you get 2.833 repeating? Fantastic. So then you add those two together, and we come up with the total distance traveled was 10.17 meters. Very good. Yeah.
You said that.
All right, so ready for a worksheet.